Good afternoon, scholars. Welcome back to another riveting installment of our journey through functions. Clearly, it's springtime since there's some sunlight behind me. Try and be mindful to block that out. But we're kind of deviating, but still remembering a lot of the content that we've been talking about regarding domain, range, increasing, decreasing behavior of functions, the degree, et cetera, et cetera. But now we're going to start looking at how can we transform functions graphically? What does that look like in context? So within today's lesson, we're going to be moving some functions, learning how to use function notation to represent a vertical horizontal translation from one graph to another so that you can describe the graphical behavior of a function in context. You'll know you've got it when you can use function notation to represent a vertical or horizontal translation from one graph to another. Let's get into it. So here we have these two functions, f of x and g of x, as you can see. Algebraically, they are very similar, almost identical, aside from one slight component. I can easily identify what that component is, but here I would like for you to describe in writing. Okay, give me some context, almost like a Google Maps per se. What is happening here? Is the function moving? Is it getting larger? Is it rotating? Right? These are things that we spoke about briefly during today's polygraph. Here we are provided with two images, f and g. We can clearly see that G is not in the same location as F, but it visually looks very similar. So first and foremost, complete this table for the outputs of G of X at these corresponding input values. If f of 0 equals negative 0.86, right, so we can identify that here on our graph. What is G of 0? So we can also look at the graph here, right, and you'll input your numerical value that you think it is. But explain how you know our explanation should be tied to this idea of a transformation. So try to establish some type of algebraic or a mathematical relationship between the function outputs of f of x and the function outputs of g of x, since those are what are changing, not the x values. We introduce a new function h of x to be the function f of x minus 2.5. So what that means is where x is negative 4, f of x is 0, so f of negative 4 was 0. So we would do 0 minus 2.5, and the output there would be negative 2.5. I'll do the easy ones. Maybe they're the hard ones. And you'll be tasked with doing the more difficult ones. The reason why this says NaN, because this is waiting for inputs from the previous table. Not saying that these are the right numbers, because I doubt that they are. But whatever you type in there will magically appear there. Call me the Steve Jobs of Desmos. Not really. So once you complete that table for h of x, you'll sketch your graph accordingly. Okay? And you might want to compare and contrast, visually speaking, what does the graph of f of x looks like compared to the graph of g of x and compared to your graph of h of x, because I would like for you to write an equation for g of x in terms of f of x for any input x. So what that means is, how can we create this graphical representation of g of x based on the function f of x? So I can clearly see that the function is increasing or being pushed, right, almost lifted vertically by approximately what appears to be 4 units. So by now, you have not deduced. If we add or subtract a constant to the output of a function, that will allow us to adjust its location vertically along the y-axis. So please take a moment and answer or create your expression for h of x in terms, or sorry, for g of x in terms of h of x, right? So once again, it's all based on g of x, right? So we'll have to look at where g of x is located. You'll have to take a look at your graph for h of x and create your expression accordingly. All right, So in this instance, we have a contextual problem where a breaking kitchen has a thermostat set to 65 degrees. Starting at 5 a.m., the temperature in the kitchen rises to 85 degrees Fahrenheit when the ovens and the other kitchen equipment are turned on to bake the daily breads and pastries. So I know that I am at 65 to start. This x-axis is hours after midnight. So from midnight to 5 a.m., it is 65 degrees. And the kitchen then rises to 85 degrees. If you're wondering why I'm not drawing a completely vertical line here, ask yourself, if you turn on the heat at your home, is it this instantaneous boom, 90 degrees, right? There's a gradual increase, so we have to represent that um, with respect to time. The ovens are turned off at 10 a.m. when the baking finishes, right? So it maintains its temperature through 10 a.m. Let me erase that. Oops, there we go. Right, so I can kind of make that should be a constant line. I don't know what the heck is going on. Um, right, but then if the ovens are turned back off, I can kind of make this assumption that, all right, at 10 a.m., the temperature will return back to 65 degrees and remain that way for the entire duration of the day. Just trying to make sure that this is as horizontal as possible. Close enough. Looks pretty good, except for this top part. All right, so there's h of x. Now we're going to make an adjustment, so select a new color, and Desmos has also given you different thicknesses for your line. But the bakery owner decides to change the shop hours to start and end 2 hours early. So you need to determine, well, now what is the new starting time for baking and ending time for baking. Using a different color, sketch a graph of that new function g, which gives the temperature in the kitchen, right? Temperature in the kitchen as a function of time. What does h of 10.25 equals 80 mean in context? I can know what the input is. I can know what the output is. Okay. But what do those numbers actually portray in our real world? Why is that reasonable? Okay. If h of 10.25 equals 80, then what would be the corresponding point on the graph of GB? We're exploring here. We're just starting out. So determine what these question marks should be, and then create an equation for g in terms of h. Right? G of x equals, how can you manipulate the function of h so that it precisely aligns with the behavior that we are experiencing in g? And that's where we'll pause and pick up together in class. See you there.